All right, here's another example of a related rate problem. I have a conveyor belt dumping sand onto a conical pile at a rate of 15 cubic feet per minute. Because of the stickiness of the sand, the pile always has its height equal to 2/3 the diameter of the base. This is not uncommon. Different types of material have a natural stickiness to them that, some of them are stickier than others, and so they, can form piles that are steeper or less steep. The more sticky they are, the steeper the slope can be before things start to slough off. Anyway, so we have a 2/3, the height is 2/3 the diameter of the base. How fast is the height of the pile growing when the pile is 10 feet high? Okay, so they give us this rate up here, 15 cubic feet per minute. That's the sand coming off. Now, that's cubic feet per minute. Cubic feet is volume, so this is a rate of change in volume. So I'll use V for volume, and T is time, T is in minutes. All right. Now, all that sand that's coming off the conveyor belt is being dumped onto this pile. So 15 cubic feet per minute is the rate at which the volume of this pile is growing. Right? The pile keeps getting bigger and bigger. Question is, how fast is its height? How fast is the height of the pile growing when the pile's 10 feet? So I'm going to need to know something about the height. Let me draw that in. And they're asking me how fast is the height of the pile growing when the pile is 10 feet high. So they're asking me the rate of change in the height with respect to time, right? That's equal to question mark when the height is 10. So they tell me one rate, they ask me for another rate, and then they give me a specific time I'm interested in here. So they give me the rate dV dt. I'm looking for dH dt. I need a relationship between the height and the volume. I need a relationship between V and H here. Well, I know that the volume of a cone is 1/3 the area of the base times the height. So this has a few too many variables in it because it's got the R and the H. But there's a relationship between R and H because they tell me something about how the height is related to the diameter. So I know that the height is always 2/3 the diameter, and I know that the diameter is twice the radius. So I have the height is 2/3 times 2r. So in fact, what I want to do is I want to get rid of the radius. I'm going to solve for radius here. The radius is 3h over 4. So what I'm going to do now is I'm going to take that and plug it in here and get a relationship that contains just the volume and the height. So I've got 1/3 pi times 3h over 4 squared times h. So the volume is, let's see, there's a pi on the top. There's a 3 squared, but then a divided by 3, which just leaves a 3 on the top. There's a 4 squared on the bottom, and there's an h squared times h, which is h cubed. Okay. So now I have a relationship between between v and h. Both of those are changing as time changes, right? As the sand keeps dumping on here, the volume's getting bigger, the height's getting bigger. So both v and h are functions of t, functions of time, and I can implicitly differentiate with respect to time here. So the derivative of the left-hand side is just dv dt, and the derivative of the right-hand side, well, the 3 pi over 16 is going to stay out there, and then there's a 3 that joins it. So 9 pi over 16 times h squared. That would be the derivative with respect to h. I want it with respect to t. So I'll multiply by dH dt. And now I have a relationship between the rates. I've related the rate at which v is changing with the rate in which h is changing. Plug in everything I know and solve for the one I don't. dV dt, they tell me, is 15. 9 pi over 16. H is equal to this is where I actually use the number 10. Right? I can't plug that in too soon because it, if I plug the 10 in up here, then I'd have the volume as a constant and the derivative would look like 0. But you gotta wait till after you take the derivative to start plugging stuff in. So I know the 15, I know the 10, dH dt is the thing I'm looking for. So here we go. dH dt is 15 times 16 divided by 9 pi, and there's 100 on the bottom. So so whatever that is, and that is, I'm going to type it into my calculator, 0.08488, and this would be in feet per minute. So not particularly fast, but by the time you got a pile that's 10 feet tall, yeah, that's a big pile. And when you dump sand on this, every minute this 15 cubic feet gets dumped on and covers up the outside, so you get this really thin layer of new sand every minute. Only 15 cubic meters, and so the change in the height there is just a very small change in height at that point. Okay. Anyway, what did we do? We knew one rate. We were asked for the other rate. We found a relationship between the variables, which is always true, no matter what the size of that cone was. There's the relationship between v and h. We could then implicitly differentiate to find a relationship between dv dt and dH dt. Plug in everything we know, solve for the one we don't.